This is the formula for the volume of a sphere. Now, how do we derive it? I'm going to be showing a method to derive it that will not require any integration or differentiation or anything complicated like that. So if you're a pre-calculus student, then welcome. And also, if you appreciate and like math content like this, please do consider subscribing. Now, I should mention that there is already a method, a good method, to do so without calculus. And this one involves splitting the sphere into many square-based pyramids, and then you just add the total volume of all the square-based pyramids. But for that one, you would also need to prove the volume of a square-based pyramid, its formula that is, and you would also need to prove the formula for the surface area of a sphere, which I think is a lengthy process. Now, in this method, there will also be a formula that you might have not known before, but that formula will not really be that hard to prove. In fact, when you see it, why don't you try proving it yourself? So now, let's begin. Our first step is to take our sphere, and we're going to now split it into several slices, like this. So you can see that we're going to split the sphere into slices all the way to the top. If you were to extract one of the slices, you would get something like this. Now the slices vary in size, however, it looks something like this. And there's like a circular area on top, right? And you can see that this is like the wall of the slice. Now notice that the slice approximates a cylinder. It isn't exactly a cylinder, but it can approximate a cylinder. Now obviously if we cut just this many slices, then that won't be, the slices will have like a curved edge because the base of the sphere is also curved. However, as you cut more and more slices, each slice becomes thinner and thinner so that the face becomes straighter, and then it approximates a cylinder better. Now, as the number of slices approach infinity, each slice will also approach an exact cylinder. So we just need to calculate the volume of all the slices and then just add them up. Now, I should note that we are first looking at the top half of the sphere. So if we just add all of these slices up, we would just get the volume of half of the sphere. And also, I should mention that the slices have identical heights. Okay, so now let's go ahead and use our formula for the volume of a cylinder. It's just pi r squared times the height. Why? Well, because a cylinder has a circular base, and if it has radius r, then its area of the circular base is pi r squared. And then now if you were to extend it, then you just need to multiply by its height to get the total volume. So that's why it's pi r squared times the height. So now for our slice, we need to identify the height of each slice. Let's quickly show that the height of each slice is just the radius of the sphere divided by the number of slices. So I'll draw a 2D view of our sphere and the slices. Okay, consider all of these slices. If you take all of their heights and then just add them up, it's just the radius of the sphere, right? And now to get the height of each slice, it's just the radius r over n. N will be the number of slices. So we know that the height of each slice is just equal to r over n. We just need to now get the radius of each slice. Now that is going to be the hard part. If you take a look at all of our slices, you notice that they vary in radius length, right? Because notice that if you were to just consider the radius of this slice over here, if I were to draw the height here, if you consider the radius of this slice over here, it's just this, right? This is its radius. And for this slice, this is its radius. And for this slice, this is its radius, and so on. So we have varying radiuses. So we need to consider the changing radiuses of each slice. So if we take the center of the sphere, right, and if we connect this center to the edge of this slice over here, so this slice over here, if we connect it to the edge of it, then notice that this is just the radius of the sphere, right? And also, if you were to connect the height like this is just the height of this triangle. You can see the triangle, right? And again, what is this height? This height is just r over n. And now notice that we can calculate the radius of this first slice. We'll call r1, because notice this is a right angle that we formed right over here. So using Pythagorean theorem, r1 is equal to r1 is equal to the square root of r squared minus r over n squared. Okay, well, how do we do this for slice number 2? Again, consider our 2D view of the sphere. Notice that if we take the center of the sphere and we draw a line connecting to the edge of the second slice, like so, this is just the radius of the sphere, and then we also draw the height. Now, in this case, we have 2 slices combined, so the height is doubled. Therefore, you would have a height of 2r over n. And then now, we just consider this triangle. This is now radius 2. Notice again, this is a right angle, so radius 2 is equal to r squared minus 2r over n all squared. So that would be r squared minus 2r over n and then all squared. Now, if you were to continue this process for r3, you get that r3 using the same technique is just r squared minus 3r over n all squared. Now, do you notice the pattern? Well, the pattern here is that notice for r1, it's r squared minus 1r over n all squared. For r2, it's r squared, inside the square root, it's r squared minus 2r over n all squared. And for r3, 3r over n all squared. So for the mth slice, its radius, we'll call rm, this is equal to the square root of r squared minus mr over n all squared. So that's the general form. And I'm going to write this here up in the corner for reference. So now that I have the general form written here, I'm going to erase all of these specific cases. Okay, so now that we have the general form up here, we're going to apply it. So what's the volume for the first slice? Well, that would just be pi r1 squared times the height. And now the second one would be pi r2 squared times the height. They have the same height. And for the third slice, you have pi r3 squared times the height. And this just goes on all the way until pi rn squared times the height. Now notice that you can actually factor out pi and h from this entire expression, so that you just get pi times h, which is just r over n. So I'm going to rewrite this as pi r over n, and then inside you just have r1 squared plus r2 squared plus r3 squared plus all the way until rn squared. So now if we were to substitute r1, r2, r3 with this formula, well then notice for r1, if you do so, then you would just get r minus r squared, minus r over n all squared, and m is 1. And for r2, m is 2. r3, m is 3, and just so on, right? Now notice that since it's all squared, you actually don't need the square root when you write it out. So this is just equal to pi r over n. Now for r1 squared, you would just get r squared minus r over n squared. For r2 squared, you just get r squared minus 2r over n squared. r3, that would just be r squared minus 3r over n squared, and then this just goes on all the way until you have rn, which would get you r squared minus nr over n squared, and close bracket. Now notice that inside the brackets, we have a bunch of r squareds. How many r squareds? N r squareds, right? So then this would just be inside the bracket. I'll erase the sphere now. We would just have inside the brackets nr squared, and then plus, now what's left? We still have minus r over n squared, minus 2r over n squared, minus 3r over n squared, all the way to minus nr over n squared. So we'll write that all down. There we go. And now we can actually expand the squares that you see here, right? So again, we'll write this as pi r over n. We still have nr squared. Now we'll evaluate for each of the squares. For the first one over here, this would just be minus r squared over n squared. For the second one, it would be minus 2 squared times r squared over n squared. For the third one, you have 3 squared times r squared over n squared. And now this will go all the way until n squared times r squared over n squared. Now notice they all have common denominator, n squared, so you can combine them. So again, now you can combine them into a common denominator of n squared, like so. And on the numerator, you just get, now for the numerator, notice that you can actually factor out r squared. So then, if you factor out the r squared in the numerator, well then you would just get r squared on the outside, and then inside you just have 1, alright, 1 squared, because 1 squared is still just 1, and then you have plus 2 squared, plus 3 squared, plus all the way to n squared, all over n squared, over here. Okay, now I have reached the point where I have to tell you about the formula. Some of you might notice already, but if you don't notice, then that's okay. Essentially, notice that on the numerator we have a sum of the squares. That is, we have 1 squared plus 2 squared plus 3 squared plus all the way to n squared. We actually have a very nice formula for this. This right over here, the sum of the squares, is equal to 1/6 times n plus 1 times 2n plus 1. That's the formula. Now, if you want to prove it, go ahead. You can use proof by induction to do this. So now let's substitute this with this. So if we do our substitution, this would be pi r times n, and inside you have n r squared, and then here you have r squared times 1/6 times n plus 1 times 2n plus 1. And at the bottom you have n squared. There we go. Now, I'm actually going to expand and simplify this numerator over here, so that's going to take me some time. Okay, so I've expanded and simplified, sort of. So now let's multiply pi r over n into the bracket. So for the first term, we would just get pi r cubed, and now for the fraction part, we just need to multiply the numerator and denominators. Okay, let's try to do this. We have 1/6. Okay. Anyways, at the bottom we have over n cubed because we have n times n squared. Okay, so now let's split this fraction up. We can split each term on the numerator up because, well, this is a fraction. So we're going to split it like this, with each denominator of n cubed. Now notice that for this one, for this fraction, you can cancel out these r cubed, right? And for this one, you can cancel out this r squared, and this n cubed just becomes n to the 1. And over here, you can cancel out this n, and this just becomes n squared. Okay, so now let's rewrite this without all of these crossings out. Okay, so I have done it. Remember from the beginning of the video, we split the top half of the sphere into several slices. And remember, as the number of slices approaches infinity, each slice approaches a perfect cylinder. So if you want to get the volume of a perfect half sphere, you need to have the number of slices approach infinity. So for this case, you need n to approach infinity, and then you have to evaluate this expression as n approaches infinity. How do we do this? This is actually not that hard to do. If I gave you the expression 5 over x, and I told you to evaluate this as x approaches infinity, so as x approaches infinity, well then you can just try certain values for x. Try x equals to 10. Okay, then that's just a half. Try x is equal to 100. Okay, well that's just 1 over 20. And try like x equals to 1,000, 10,000, 1 million, so on and so forth. As the number of x gets larger and larger, the entire expression becomes smaller and smaller. Particularly, it becomes closer and closer to 0, right? So we say that the limit, we write it like this, the limit as x approaches infinity, this is actually just 0. So then, likewise, notice that for this expression as n approaches infinity, this term and this term would be 0, right? Because notice as the denominator gets larger and larger, the entire fraction gets smaller and smaller, closer to 0. So now, as n approaches infinity, the entire expression we are left with is just it's just pi r cubed minus 1/6 times r cubed times pi times 2. So now if we evaluate for this, notice that we have a 2 here, we can just cross reduce. So all we are looking at is pi r cubed minus 1/3 pi r cubed, like this, right? So then, if you were to evaluate this, what you would actually get is 2/3 pi r cubed. But wait a minute, that isn't the volume of a sphere. Well, remember, we only took the top half of the sphere, so in order to get our total formula, we just multiply this by 2, and then we should get 4/3 pi r cubed, and that is our answer. So that's how you can derive the volume of a sphere without any integration. Okay, well, that's going to be all for this video. If you appreciate and like math content like this, well, please consider subscribing. Thank you.